Welcome to this first video for sections 3.2 and 3.3, where we're going to be looking at the FTC, which is the fundamental theorem of calculus, and some basic rules for integration. So let's set this up by going back and recalling that when we take the integral of a function f of x over some interval that starts at a and ends at b, we said that this was the signed area between the function, the graph of the function f of x, and the x-axis. So if the graph of the function was below the x-axis, then the area here in red would count as negative area. If the graph is above the function, then this area in blue would count as positive area. And then you would have to add up all of the negative areas in red. There's two of them in this particular picture, and any positive areas in blue to get the actual integral, which is the signed area. So essentially we said that the integral, this was the integral symbol, from x equals a to x equals b of the function f of x dx, remember we need that dx, is equal to all of the area that's above the axis minus all of the area that's below the axis. And so the integral will calculate that for us. And so our task in this particular section is to find out how to efficiently calculate this integral. So the question is, how do we calculate this? In the previous section, we looked at adding up a bunch of areas for rectangles, which got pretty tedious because you have to calculate a bunch of different little areas. So if we don't want to estimate this area with rectangles and instead want a more accurate and more efficient way to do this, then what we're going to basically do is we're going to say, let that integral of that function be equal to this weird looking thing. Now let's just break this up a little bit. Let's just forget about the limit for a moment and just focus right here. This says take the sum from 1 to n of this set of products. So remember, delta x was the width of each rectangle, and f evaluated at some x value was the height of the rectangle. So really what I'm doing here is multiplying the base of the rectangle by the height of the rectangle, and then I add up the area of all of those rectangles. We start at the first one, then we do the second one, the third one, the fourth one, the fifth one, all the way up to the nth one. So if we had 50 rectangles, we would have to do 50 calculations and add them all up. Now, if we want that area to be more precise, we would let the number of rectangles get larger and larger, which would mean that they would get more skinny and more skinny as the number of n rectangles got larger. Of course, we can never get to an infinite number of rectangles, but as we've seen before, this limit tool allows us to ask the question, well, what happens if n gets closer to infinity? So what we're basically asking here is, if we let the number of rectangles get very, very large, then what does the sum of each of those individual rectangles add up to? And of course, the more rectangles we have, the less error that we're going to have in those rectangles being too large or too small, as we saw before. So this is going to give us the proper area or the integral. So the question becomes, how do we do this? So it turns out that there's a pretty easy way to do this, and it's called the fundamental theorem of calculus, otherwise known as FTC. Clearly, because it's the fundamental theorem of calculus, this is pretty important, and it is. It's the central theorem in a basic calculus course, and it says the following. If capital F prime is equal to little f, and f is continuous on some interval ab, then the integral that we're looking for of the function little f is equal to capital F evaluated at b, the upper limit of integration, minus capital F evaluated at little a, the lower limit of integration. Now, we're going to have to think a little bit about the difference between little f and capital F in a minute, but what I want you to notice here is that the integral is being boiled down, so to speak, to the difference of two simple calculations. So if I know what capital F is, then I can simply plug in the two limits of integration, always the upper limit that's up here first, minus capital F at lower a, and that's going to give you the signed area of that function, little f. So we call capital F the antiderivative of little f. And the condition is up here. If I'm starting with little f, then whatever big F is, when I take its derivative, I have to end up with little f. This is going to make more sense as we do some examples, but we have to be very careful that we think about what we're doing here. We're starting with little f, that's what we're taking the integral of, and that's going to require that we go and find some big F. And the way we're going to know that we've got big F correct is that the derivative of capital F is equal to little f. Right? So basically this boils down to this. We need to find a function, capital F, whose derivative is little f. In other words, capital F primed is equal to little f. If we can do this, if we can find that capital F, that antiderivative, then we can evaluate it at x equal a, then x equal b, then we subtract them, and that's going to give us the signed area, which is the integral. In terms of notation, this difference right here is sometimes denoted with capital F of x, and then we put a vertical slash, and then we put b and a here. So we'll often use this as we work through the problem, and we'll see here in a moment. So there's two different ways to write this, but keep this in mind as we make our way through the following examples. Okay, so before we get to some actual integrals, we want to talk about finding actual antiderivatives. So for example, let's say we want to find an antiderivative for little f equals 6x to the fifth. In other words, we want to find some other function, capital F, such that the derivative of that capital F function is equal to 6x to the 5. So what does the job? One obvious candidate is just x to the 6th. Let's think about this. Remember, the derivative of this capital F has to be equal to little f. And because we know with the power rule, when we take a derivative, we reduce the power by 1, then going backwards to find the antiderivative, the opposite of the derivative, it would make sense that we're going to increase the power by 1, which is why I chose this. So here's how we would check this. We would say, what is the derivative of big F? It is 6x to the 5. Well, if that matches little f, then we know we found little f's antiderivative, which we call capital F. But are there others? For example, take a look at this one. Capital F is equal to x to the 6th plus 2. Well, the derivative of this function is 6x to the 5 plus what? The derivative of a constant is 0. So the derivative of this function is still 6x to the 5. So both of these are candidates for capital F. Here's another one. Here's capital F equals x to the 6th minus 7. The derivative of this constant, negative 7, is going to be 0. So it's going to wipe out the constant term and leave me with a derivative of 6x to the 5. So that one works. In fact, any constant, like the square root of 3, or pi, or e, any constant can be added to the end of this x to the 6th, And the derivative of the resulting function will still be what we're looking for. So what this means is that capital F is not unique. There are many candidates for capital F. And so we have to think about how do we express that. And the way we do it is we say that capital F is equal to x to the 6 plus some arbitrary constant c. And we call this the antiderivative of f. These are all individual antiderivatives of little f. This one we call the antiderivative because it captures the idea that we can add any constant to x to the 6th and still end up with what we're looking for. So that is the idea of an antiderivative. In the next example, in the next video, we're going to take a look at how to apply this rule across different examples. So once you finish this video, go ahead and start the next one for example 1.